Okay, good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to continue the 10-1. Basically what we learned yesterday was the Radius-Chord theorem. What does that basically state in a nutshell? If I have a chord here, okay, we'll call this chord AB, and from the center I have a radii that creates a perpendicular to that chord. A couple things happen. The chord gets bisected, vice versa. If I have a radius that bisects a chord, then I create a 90-degree angle. We went ahead and proved why all of these theorems were valid, and that's basically, in a nutshell, what's going on. Oh, and we also stated that if you have a segment here that is perpendicular bisector to the chord, then it's going to be going through the center point because of the converse of the perpendicular bisector theorem. Okay, so now let's get to work. Let's do some examples here today. For this first one, guys, we're going to do a little bit of proofs. The good news is this is the end of proving hardcore stuff. We're just going to have a few proofs here at the end. Most people like the proofs, though, so it's bittersweet for some of us. So anyways, first statement, my friends. Circle Q, and they're stating that PR is perpendicular to ST, so of course, that's my given. Let's go back in time. Remember that when we have a fact, let's go ahead and label it. That's the best way, in my opinion, to work with this. So if this is PR is perpendicular to ST, then I'm creating 90-degree angles here, right? So I can say, since it's perpendicular, I can say that PR bisects ST. Why? Well, if a radii is perpendicular to a chord, it bisects the chord. Okay? We gave these names yesterday. They're all kind of the same. It's a Radius-Chord theorem. It's kind of hard to determine which one. Is it number 1, number 2, number 3? So why don't you just, for this one, since we're already wrapping up proofs, let's go ahead and do it the long way, okay? If a radius is perpendicular to a chord, then it bisects the chord. So if it bisects the chord, then we know that SR is a perpendicular bisector to ST. Why? The perpendicular bisector theorem. Okay? Now, a lot of you may maybe say, wait, he skipped a lot of steps here. Yeah, I kind of did. At this point of the game, I could have put, and you're not going to get anything discounted for this, you could have said PRS and PRT are 90-degree angles. Definition of perpendicularity. You could have said PRS and angle PRT are congruent. 90-degree angle, right angles are congruent. You could have said SR and RT are congruent. Definition of bisector. Then PR is a perpendicular bisector to ST. I skipped there as well. Why is it the perpendicular bisector theorem? Well, we know that if you have 2 points that are congruent to the endpoint of the same segment and perpendicular, it's going to be the perpendicular bisector. Okay? And then I can prove that PS is congruent to PD, PT. Why? Because if a point is on a perpendicular bisector of a segment, then it is equidistant from the endpoints. So what basically happened here was, since QR is a perpendicular bisector of ST, okay, this point P is on this perpendicular bisector, so therefore PS has to be congruent to PT. Yes and yes. Because at this point we're not really using, it is kind of the converse of the perpendicular bisector theorem. If you put that on a test or a quiz, I'm not going to mark that wrong. Technically, I'm trying to teach you, though, that it's coming from what we just learned, the Radius-Chord theorem. But I'm not going to mark that wrong because technically you're 100% right. Yes, sir. Equidistance theorem would be wrong. Thank you, though, sir. Yes, sir. Now, at this point, I could prove that the triangles are congruent not by side angle side, but by HL, right? Or actually, you could say that PR is congruent to PR reflexive, and then say that triangle PRS is congruent to PRT because of side angle side. Yes, you could have done that. A lot of different things going on here. More than one way to skin this cat. Yes, sir. You wouldn't have to point out that it was reflexive at this point. Okay? The reason I'm being a little bit lax with you guys is not because I'm trying to make it easier, but I believe in you, and I know that these things are pretty much common knowledge now. On the SAT, they're never going to ask you for a proof, or at least for this SAT. Now, we'll see what happens when you take your SAT. There's going to be a different SAT now, and there's going to be different math sections, so I got to study that and see if there are going to be any proofs. If by chance there were proofs on the SAT, I would not skip a single step. Okay, I would use reflexive. I would state, hey, this angle is a right angle because definition of bisector, but for our intents and purposes, we're pretty good here. Does that make sense, gentlemen? All right, let's look at some practical applications now. This is the fun part. This is what I enjoy about circles. The radius of a circle O is 13 millimeters. The length of chord PQ is 10 millimeters. Find the distance from chord PQ to center O. Okay, this is going to be a real simple one. We know for sure that the radius is 13, correct? You with me here, gentlemen? So that's 13. These two are both congruent because all radii are congruent, correct? Now, we also can draw a radius O going through this point R. You with me here? If I do that, if a radius goes through a chord and it's coming from the center, what does it do to that chord? It's a perpendicular bisector to it. So basically that comes out and this gets split into half. So if PQ is 10, wouldn't this be 5? So what is the distance from R to O? 12. It's a 5, 12, 13 triangle. So that would be 12 millimeters. Does that make sense? This is very important for you guys to understand that. That's the power of this theorem. Okay? And if any, teacher or anyone else said, "Oh, but why?" We can prove why very easily. Okay? Remember that if I draw an altitude here, okay, automatically, if there's an altitude there, it's perpendicular to the chord. That means that automatically it bisects this chord. And then we have the Pythagorean triple. That's like heavy math. That's really simple. Most people would not be able to do that. If people did do that and they guessed, that's all it would be for them. It'd be a lucky guess. And God bless you, that's awesome, good for you. But we know why. We know why, because if I draw an altitude, I bisect this chord. That's the Radius-Chord theorem in action. Sir. Okay, so anyways, let us continue, okay? Hold on, give me 1 second, please. All right, sorry about that, guys. Okay, my friends, let's check this one out. This is actually a pretty cool proof. Triangle ABC is isosceles. So, they gave you a little hint. AB is congruent to, that's wrong. Yeah, no, AB is congruent to AC, yeah, because they're talking about triangle ABC is isosceles. So AB is congruent to AC. Awesome. There's circle O and there's circle Q, and they say that BC is parallel to PQ. So that means that this guy is parallel to that guy. Okay, so let's knock this proof out. It's a nice proof, nice and long. It's good stuff. So let's try our best to figure this one out. Okay, of course we have the triangle ABC is isosceles. That's a given. Okay, that's awesome. O and circle, yes sir. Okay, give me 1 second. Circle O and Q, circle P and Q are present, and you have BC is parallel to PQ. So we know that this and this, and we know that this is parallel to this. Okay, you wanted to get a shot on that one? Angle ABC is congruent to angle ACB. Yeah, that is true. I don't know if it's the next one right off the bat though, but I think you're pretty on track. You're going the right way. I don't think that if you would have said that at first, it would not have been wrong. What we want to see though immediately though is that if BC is parallel to PQ, then that means this guy is congruent to this guy, and this guy is congruent to this guy. Why? Because exactly, corresponding angles are congruent. Yes, sir. No, you would not need to do that. You don't need to work with supplementary at this point. Now, at this point, I think we go back to what you had said. Now, angle ABC is congruent to angle ACB because if sides, then angles. So now pay attention, guys. If we've got angle ABC is congruent to APQ, and angle ACB is congruent to AQP, and we have that angle ABC is congruent to ACB, then what does that tell you about everything? What can I determine there using a little transitive property? Now I messed up. That angle P would be congruent to angle Q as well. Think about it, guys. If this guy is congruent to this guy, and this guy is congruent to that guy, but B is congruent to C, then that means by transitive property, P is congruent to Q. Transitive. Now, if those two guys are congruent, guess what? Now I can say that AP is congruent to AQ because if angles, then sides. And now if I say that, let me go ahead and clean this up a little bit. Basically, now I said that this is congruent to this. But we had stated from the beginning that AB is congruent to AC, right? So what do I know now about PB and CQ? They're congruent. Why? Because of subtraction property. Very good, my brothers. And now if PB is congruent to CQ, aren't those radii? And if radii of different circles are congruent, what do we know about those circles then? Abso-freaking-lutely they're congruent. Because circles with congruent radii are congruent. Yes, sir, my brother. Could you have proven BC PQ as an isosceles trapezoid? At this point, it would not have helped you, but yes, absolutely. I mean, absolutely. You could have said it was an isosceles trapezoid, and then you could have said PB is congruent to CQ because definition of isosceles trapezoid. But I mean, you'd be proving this already and then going beyond to go back. So, but there was nothing wrong with what you said. Yeah, I'm very proud of you. Well done. That was a good proof, right? Very, very good stuff. Okay. May I continue? This class is definitely we're close to spring break. I can feel the tension in the air. All right, let's do this. Oh, that's it. We're done. All right, guys. Thank you very much. Have a great day, and I hope you learned a lot. Bye-bye.